Hey, this is video 25.4. We're looking at the electric potential due to continuous charge distributions, meaning not created of point charges. So for instance, an amorphous blob with charge on it. But the thing is, we can treat it like an infinite number of very closely spaced point charges, and we'll call those charges each dq. And if we're trying to find the potential at this point P here, the distance to dq we'll say is r. And so the potential due to that bit of charge, which we'll call dv, is equal to k times dq divided by r. And then, to find the total potential, we'll integrate all of the dv's, which is k times the integral of dq over r. Integrals just being Riemann sums. Some things you'll need to remember for this, for particular charge distributions, are the ideas of linear surface charge densities. Linear charge densities, remember, is the charge per unit length. Surface charge density is the charge per unit area. Volume charge density you don't need to worry about for this particular case. So let's look at an example. Let's say we have a ring of charge, total charge Q, radius capital R, and we want to know what the potential is at a point on its axis. And we'll call that point P here, and we'll say that's at a distance z above the center of the ring. So what we do is we break the ring up into a bunch of small point charges dq. The distance that they are from point P is little r. And we can say, because we've got a right triangle here, that r squared is equal to big R squared plus z squared. And that means that we can say that the potential due to dq is k times dq divided by square root of big R squared plus z squared. And you may think, oh, we're in for another terrible, terrible integral, but it turns out we're not. Because when we go to integrate this, we find that k is a constant, big R and z are constants because those don't change for each dq. Big R and z, and therefore little r, are the same for every single dq. So all of that comes out of the integral as well. So we just have the integral of dq, and that is just the total charge. So the electric potential is just kq over the square root of r squared plus z squared. Very, very straightforward. Now, in chapter 23, I think, there's a derivation for finding the electric field at point P, and it's a huge pain. Well, it's actually not that bad, but it's mathematically intensive. Now, there's another way of getting the electric field, and one of your homework problems asks you to do that. And this is why we like electric potential, because remember, the electric field in the z direction is dv dz. So really, all you need to do there is find the derivative of that, and that gets that particular homework problem. And let's see. Your book has a derivation of potential due to a line of charge, page 576. Have a look at it. It's mathematically interesting. Don't worry about the potential due to a charged disk. That's not going to show up on the AP exam, and it's kind of a pain. For tomorrow, I'm going to check question 5 and also problem 25.